Hey, Arjun.
Hello, Professor.
Hey, how's it going?
Pretty good. How about you?
Good, good.
Oh man, this semester has been just sort of unproductive for me. Just everything online. I don't know.
Yeah, it's tough. I know. It's weird because I feel like I save so much time every day because I don't have to commute or like get dressed in the morning, but then I feel like
Oh
so much less productive because I'm at home.
yeah. For me, I just kind of waste too much time playing video games. Correct? Oh, correct. Professor, will today's lecture be another ANSYS tutorial on like just an example, or will it be the like a derivation and example handwritten?
Yeah, so we're still going to be in the theory for a while. So our next ANSYS activity is not going to be until week 6, actually. And so
Oh,
this
okay.
this first part of the class we're going to focus mostly on the theory, and then the ANSYS stuff will kind of ramp up more towards the second half. And that's when you guys are working on your projects. So that's I kind of time it like that. Yeah.
Gotcha. Okay.
Mhm.
Hello.
Hey.
Quick question. I think I saw in your 442 class we're gonna get into medical imaging of some sort, or we might cover it
Yeah, that's going to be next week.
next week. So we're gonna be going over like MRIs and CAT scans and things of that nature.
Yeah, so we're just going to talk about it just kind of in general. So I don't have the expertise to really dive into how those things work, but yeah, I want to go over that before we do our first workshop in Symbascular, because it'd be helpful to know what a CT scan is, what an MRI scan is. But,
Okay.
Yeah.
Because I just just to share a little bit about what I'm doing for my thesis. I am doing something related to that, but
Okay.
it's with artificial intelligence.
Oh, great, awesome.
I'm using neural networks to piece together these images of the brain or the heart of all these organs.
Cool.
Yeah, maybe I could share a little bit more some other time, but
Yeah, no, that sounds awesome. Who are you working with?
Dr. James.
Okay, nice, awesome.
Yeah, like he has no expertise in it either, but he said just go for it because it was related to manufacturing.
Uh-huh.
Yeah, I'm trying to apply it to manufacturing.
I see.
Yeah. Anyway, that's it for me.
Nice. No, it's awesome. Yeah, he definitely likes to engage in those projects. So I've been on the thesis committee for a couple of the students, and their projects are really varied. So it's cool.
Oh.
It's cool that he's he's willing to jump in on those projects like that.
Yeah, you might be there for my defense. I'm defending later this semester.
Okay. Yeah.
Yeah.
Yeah. If you want me there, then just let me know.
Oh, that's another thing. I heard that I get to pick who's there. Is that true?
Well, I mean, I don't want to. I think Dr. James, lets students pick, but I know I don't want to pick. I don't want to speak generally for all advisors, but usually yes.
Oh, okay, cool.
Yeah, I think Dr. James lets the students pick, but if they don't want to pick, then I think he can suggest some people too.
I'll follow up with him on that. We'll see.
Okay. Yeah. I'm pretty sure he lets you guys pick. I let my students pick. I only give them input if they ask me for it.
Okay.
Are we continuing off the Truss notes?
Yes. Yeah.
Okay, cool.
Okay, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good, thank you. How are you?
Good, good. Yeah, end of the week. So it's end of week 3. So I know things are probably getting really busy for you guys already. So, you know, definitely the semester is in full swing. You just woke up. I see. You're one of my friends is like that too. So she wakes up like you know, like 4 or 5 o'clock, and then she works through the night. She's an engineer, by the way, so it's not like, you know, she has a night shift job or anything like that. But her schedule is just totally flipped, which is fine most of the time. But when we want to hang out with her, it's difficult because we have to plan for the fact that she doesn't wake up until 4 or 5. Yeah, it's not the fact that she's an engineer; it's just that she just likes sleeping during the day. Yeah. Okay. So hopefully the internet stays up for the entire lecture today. So I apologize last time for cutting it off a little bit early, which was a little bit strange. So I right after the lecture I had to call Spectrum, and they had to reset my whole connection and everything like that. So, you know, hopefully it's stable today, so, you know, we can get through the lecture. Because the plan for today is we're going to continue on with our lecture notes on truss systems. Okay, and so last time we saw how we solve 1D truss problems. Today we're going to be spending all day learning about 2D truss problems. Okay, so we started a little bit of it at the end of lecture last time before we got cut off by Spectrum, but, you know, we're going to continue that today. Okay, and what I'm hoping for is we get through a good part of it, and then we finish it up next Tuesday. Okay. Any questions on that, or just anything before we get started? Okay. So I have been getting a lot of questions about, you know, when the next ANSYS activity is going to be. So I do want to address that before we begin. And so, you know, the way I kind of structured this class is I kind of front loaded a lot of the theory, right? And so this class is interesting because we kind of have to balance both, you know, the theory behind finite elements and also, you know, the practical application with ANSYS. And so I front loaded a lot of the theory because, you know, the sooner we learn the theory, the more the stuff later down the line makes sense. Because if you think about, you know, our first ANSYS activity, you know, I had you guys make a lot of decisions about, you know, how many elements to choose and what shape of the elements, you know, without really going too much into explaining why that is, right? And so I want to talk about all the theory first so that we can kind of understand those before we really get rolling with ANSYS. And so, you know, our next ANSYS activity is not going to be until week 6, but starting in week 6, we're going to have an ANSYS activity basically every other week. Okay. And so, you know, we're going to be in the theory for a while, but that's mostly just to make it so that all the rest of the ANSYS activities make more sense, and we can kind of explain every single step. Okay. Because the thing with finite elements, I think that a lot of people, a big misconception about that is that, you know, you can just go in and use the software, but you know, if you're going to end up using finite elements professionally, you know, not only do you need to know how to, you know, operate the software, but you also need to explain, you know, the decisions that you're going to make, right? Because the difficult thing with any kind of computational work, whether it be finite elements or, you know, anything else, is justifying to people that what you're simulating is actually correct. And that's actually the most difficult thing about running simulations. So there's a saying out there where, you know, if you end up doing like physical tests and experiments, then, you know, you show those results to people and everyone will believe your results except for you. But then when you run simulations or do any kind of computations, nobody will believe your results except for you, right? And so the difficult thing about, you know, using finite elements professionally is getting people to believe that what you're doing is actually legit. And to do that, you know, you need to, you know, kind of understand the theory behind it. Okay. Okay. So let's go ahead and pick up where we left off. Okay. And so we were doing Truss equations in 2D. Okay. And I believe what we just finished talking about was our two coordinate systems, right? And so we had one coordinate system called the local coordinate system. Okay. And our other coordinate system was the stationary coordinate system. Okay. Okay. And the difference between them was something like this, right? And so, you know, from here on out, we're gonna consider truss elements that can be rotated with respect to the horizontal, right? And so let's say that we have, you know, a truss element that looks like this, okay? And then if you compare that to the horizontal, you've rotated it according to an angle theta, okay? All right. And so the local coordinate system will be aligned such that it matches up with the element, right? And so you might draw the x-axis like this down the length of the bar, okay? And then its corresponding y-axis will be perpendicular to that, right? And so remember, for the local coordinate system, we give those a hat just to kind of remember that those are local. Whereas the stationary coordinate system, you know, the stationary, we give it that name because it's not going to move. So usually this is specified such that it's you know, in some kind of useful reference. And so usually the reference that we pick for the stationary coordinate system is the x-axis is, you know, completely horizontal, and the y-axis is completely vertical, just from kind of a fixed reference frame. Okay. All right. And so what you'll end up seeing is that, you know, when we start to solve these problems, we're going to have multiple truss elements, you know, interacting together like this. Okay. Okay. Maybe, you know, another truss element like that. Okay. And so all the truss elements are going to be rotated in different directions. Okay. And so because of that, each of these trusses will have their own unique local coordinate system. Okay. You know, they all have their own unique one because they're all rotated differently, right? So they all have a different orientation. And so this is kind of a problem because right now what we have, you know, we have an expression for the element stiffness matrix for a truss element, but that's only within, you know, its local coordinate system, right? For now, can only formulate element stiffness in local coordinates. Okay. And so we can find the element stiffness of each of these guys in their own local coordinates, right? And that's fine. But then when we want to combine all of these guys together into our global, element system, remember the part where we kind of insert the matrices into the different parts, we can't do that because they're all part of their own local system. So it's not really, you can't really just combine them all like that. And so our goal here, and kind of the reason why we have the stationary coordinate system, is so that, we can take these element stiffness matrices and combine them all into, one unified system. Okay. And so the first part, the first thing that we'll go over is how do we take the element stiffness matrix for a truss, which is in its local coordinates, and how do we transform that into, or I should say, rotate that into the stationary coordinates. Okay. Okay. Any questions on that so far? Okay. All right. And so let's go over how we can do that. Okay. And so first, let me just draw just an arbitrary vector. All right. So we'll call this vector u. Okay. And this is a vector that's kind of pointed in an arbitrary direction. And let's write out the components of u in both coordinate systems. Okay. And so let's say that we have our stationary coordinate system that looks like this. Okay. And so we have our x and y, right? And so we can draw out the components of this vector in this system, right? Right. So we can basically say that u is equal to ux, uy, right? Those are just simply its x and y coordinates. Right? But at the same time, if we have a local coordinate system, and let's say that it's kind of arbitrary like this, okay? So this is x hat and y hat, okay? We can write out the same components of this vector in this local coordinates, okay? And so another expression for u, we'll say that this x component right here is going to be ux hat, and then the corresponding y component is going to be uy hat, okay? Okay. So it's the same vector u, right? So the vector u isn't changing here. The only thing is we're observing it from two different points of reference, right? And so we're observing it, first from the stationary coordinates, and so that's how we get ux and uy. Then we're also observing it from the local coordinates, which gives us ux hat and uy hat. Okay. Right. But since these both describe the same vector, okay, since they both describe the same vector, obviously, these two things should be related. Okay. Okay. Or in other words, there's a transformation that we can apply to transform from one vector components to the other. Okay. All right. And then let's say that one thing that we're going to need for this transformation is we need to know how these coordinate axes are related. And so let me draw this angle theta, which is right in between those two. Okay. So the angle theta is basically the angle in between the stationary x-axis and the local x-axis. All right, so the question is this like a change of basis? Yeah, you can kind of think of it like that. Yeah, you can kind of think of it like a change in basis. And actually, you might have seen this exact thing that I'm going to do. It's just that in finite elements we kind of explain it a little differently. Okay. Okay. And so in order to perform this change, or in order to perform this transformation, we're going to use what's called a transformation matrix. Okay. Okay. And so on one side, let's say that we have ux prime or ux hat and uy hat. Okay. And then on this side, we're going to have ux and uy. Okay. And so we have the on the right-hand side of the equal sign, we have the components of the vector in the in the local coordinates. On the left-hand side, we have the components of the vector in the stationary coordinates, right? And the way that we can equate them is we can apply this transformation matrix right here, okay? Right? And so if we take this transformation matrix, okay, if we take this transformation matrix and we multiply it by the components ux and uy, that will give us, the components ux hat and uy hat, okay? And you can see all of this is based on the angle through which they're related, right? And so this angle right here in between them is key. And so if we take cosine of the angle and sine of the angle, this will help us basically determine, each of those relationships. Okay. And since we're going to use this matrix, a lot in the coming pages, let me give it a symbol just for now, and I'll give it the symbol T. Okay. All right. Any questions on this? Okay. All right. And so let's take this transformation matrix and let's apply it to our element stiffness matrix for a truss. Okay. Okay. And so let's say that we have an arbitrary truss element like this, okay? And then, just like we saw in the 1D case, we're going to have the nodal forces, right? And so let's call this node 1. We'll call this node 2, okay? And so on this truss element, we're going to have F1 hat and F2 hat, okay? I'm going to give it hats because they're, we're going to put this in the local coordinates, right? In particular, these are going to be the forces in the local x direction, okay? And then if we apply our forces, we're also going to have our displacements, right? And so we're going to have u1x hat and u2x hat, okay? And so if we write out the element stiffness matrix, we get the following, right? And so we have f1x hat, f2x hat is equal to AE over L times 1 minus 1 minus 1, 1, U1x hat and U2x hat. Okay? Right. So that's just the element stiffness matrix for a truss that we worked with on Tuesday. Okay? But now that we've introduced this idea of the local and the stationary coordinates, now we can put hats on all these guys because these are all in the local coordinates. Okay. Okay. And so now what we want to do is we want to transform this element stiffness matrix so that it can be in the stationary coordinates. Okay. Okay. But before we do that, we need to actually expand this matrix system first, right? Because if you notice here, we have both nodes 1 and 2, right? And so we have F1 and F2, U1 and U2, but all these are only in the X direction, okay? And so we need to expand this so that it includes the Y direction as well. And so for right now, you know, we don't have any displacements in that direction, but we kind of need to put placeholders there so we can actually apply our transformation matrix. Okay? Because right now we don't have anything in the y hat direction. Okay? We don't have anything in that direction because it's 0, but we at least need to put placeholders there so that we can apply our transformation matrix. Okay. Because right now we can't do that because everything is in the x direction. Right? And so, you know, I'm going to write down this exact same system, but I'm going to put placeholders in there for the y direction. Right? And so instead of f1 just having f1 x hat, okay, now I'm going to have an f1 y hat as well. Okay. Okay, so similarly for node number 2. So node number 2, we're going to have both f2 x hat and f2 y hat. Okay. Right. And I'll show you the element stiffness matrix in a second, but let's write out the displacement vectors as well. Okay. And so we're going to have u1 x hat, u1 y hat, u2 x hat, and u2 y hat. Okay. Right. And so from here, we're just going to write down, you know, the entries in the matrix. So, you know, I know that we've expanded the system to include y, but since y wasn't in the original system, you know, we can just place zeros whenever, you know, we have a y term. Okay. And so the expanded matrix looks something like this. Okay. And so you can see here that, you know, we have our four, you know, our 4 ones here. So we have 1, -1, -1, 1. They're just kind of shifted over just so that we've made room for y, right? And so you can see that this one right here went right here. This -1 here went right here. This -1 here went right here. And then this one went right here, okay? And so everything is still there from our original one. We just place some additional placeholders for the y coordinate stuff. Okay. Okay. Any questions on this? Okay. All right. And so now that we have this expanded system, we can start to think about transforming this into the stationary coordinates. Okay. And so we need to do 2 transformations. So we need to transform both this f vector, okay, and so and also this solution vector right here, right? So basically anything with a hat, we need to transform it so that it doesn't have a hat anymore, okay? So no hats in here. It's like we're all going to watch a movie, so no hats in the theater. Okay, and so you know, in order to transform those hat quantities, we need to apply our transformation matrix that we talked about before, right? Because if you remember, our transformation matrix looked like this. Okay. And so if we have a vector, you know, u x hat, u y hat, we can transform it into the stationary coordinates by multiplying by this matrix right here. Okay. Right. Where this is our transformation matrix T. Okay. And so since I'm going to be writing this a lot, I'm going to use shorthand notation for this. So instead of cosine theta, I'm going to use just a C. Sine theta, I'm just going to use S. Sine theta, I'm just going to use, you know, S again. So that's going to be minus S, and then cosine theta. Okay. Right. And so I'm going to use this shorthand notation just because it's a little bit easier to write. Okay. Okay. And so now let's apply this transformation matrix to our vectors on the previous page. Okay. And you can see we actually need to apply it twice, right? Because we have two sets of vectors here. And so we have the vector for node 1, and we also have the vector for node number 2, okay? And so we need to apply our transformation matrix twice. And this is how we're going to do it. So let's take the u vector first. And so for the u vector, we have u1 x hat, u1 y hat, u2 x hat, and u2 y hat. Right? And in the end, what we want is this. Okay. In the end, we want the same vector components, but in the stationary coordinates. Okay. And then we're going to multiply this by an expanded version of our transformation matrix. Okay. Okay. And so the way that we obtain this is we basically insert this transformation matrix into the appropriate slots, right? So first thing we know is that u1 hat and uy hat, they're going to be transformed with u1x and u1y, okay? And so in order to do that, we need to insert the transformation matrix into this kind of box right here, okay? Okay, so we're going to have CS minus S and C, okay? And so that's the transformation for the first node. And then for the second node, the components at node 2 have to interact with the same components at node 2. Okay. And so in order to do that, we place another transformation matrix here. Okay. Okay, so this is going to be C, S minus S and C. Okay. And then everything else in here is going to be 0, right? And so the reason the rest of this matrix is 0 is that, we don't want stuff from node 1 to interact with node 2, right? And so, things that are in these, this top right of the matrix and the bottom left, that basically ensures that, when we perform the transformations, it's only from node 1 to node 1 and node 2 to node 2, okay? All right. Any questions on this? Okay, and so that's the transformation for U. We can do the exact same thing for F, okay? Right, and so again, we're going to transform this F, all these F hats into Fs without a hat, right? So it's going to be F1x, F1y, F2x, F2y, okay? And then in here, we're going to have the exact same components. Okay? And so let's take these expressions and then plug them into our element stiffness matrix from the previous page, okay? And so we're going to plug in for, the F hats and the U hats here, then perform some arithmetic, and then that'll give us our element stiffness matrix for a 2D truss, okay? Okay. And so when we plug in, okay, when we plug in, we get the following, right? So first we're going to plug in for, the F hat vector. And so that's going to give us CS minus SC 0, 0, 0, 0, 0, 0, 0, 0, CS minus SC. Okay. And since we plugged in for the F hats, now we just have Fs without the hat. Okay, so we have F1x, F1y, F2x, F2y. Okay. So now all these F components here, those are in the stationary coordinates. Right? Next, we're going to multiply by our element stiffness matrix. So this guy doesn't change, right? Okay. And then to this, we're going to multiply by our transformed U hat. Okay. And so over here is going to go C S minus S C 0, 0, 0, 0, 0, 0, 0, 0, C S minus S C, and then the U components in our stationary coordinates. So it's going to be U1X, U1Y, U2X, U2Y. Okay. So these don't have a hat anymore, so that's good. Okay. Okay. And so now that we've kind of plugged in for all of these guys, we can go ahead and let me replace these with some symbols so that you can kind of see all the matrix stuff that's going on. Right? And so in red right here, I'm going to call this our transformation matrix T. Okay. In green, I'm going to make that this matrix right here. So this will be our K. And I'll put a hat over it because it's our K matrix from our local system. Okay. Okay. In blue, right there, that's going to be our stationary force vector. Okay. And then in here, this is going to be our stationary displacement vector. Okay. And so, replacing these with their symbols, we have T times F is equal to K times T times U. Okay. Right. And I regret using so many different colors like that. Okay. And so ultimately what we want is we want to have a relationship between F and U. And so let's take this transformation matrix on the left-hand side and let's move it over to the right. Okay. And to do that, we're going to multiply by T inverse, right? Because remember, we're working with matrices here. So in order to cancel out one matrix on one side, you have to multiply by the matrix inverse. Okay. And so the result of that is going to be F is equal to T inverse times K times T times U. Okay. Right. And so now what we have right here is, F is equal to some stuff times U. Okay. And so if I took this group of terms right here, this T inverse times K times T, we can define this as our new element stiffness matrix. Okay. And so if we perform kind of the matrix multiplication for all these guys, then we're going to get an expression that we can use for, for a 2D truss element. Okay. All right. And so before I write down that expression, I'm going to note here that since T is kind of a special matrix as a special format, instead of doing T inverse, because T is kind of special, we can replace this instead with T transpose. Okay. And so if you just simply transpose our transformation matrix, this is kind of the same thing as doing that. Okay. Okay. And so I'm not going to go through, all the arithmetic of doing the transpose and all the matrix multiplication, but I will show you the result. Okay. But I at least wanted to show you, how we got this result, because it's going to be a little bit intimidating because it's going to have a lot of sines and cosines. But I basically wanted to show you kind of where it came from. Okay. Any questions on this? Okay. And so if we perform all of those matrix multiplications, we're going to end up with the following 4x4 element stiffness matrix. Okay? And so this is the element stiffness matrix. For a 2D truss. Okay. All right. And so remember, the way that we got this is we're going to do T transpose times K hat times T. Okay. And if we perform that multiplication, we end up with this. Okay. And so we have AE over L, right? And so remember what those stand for. So A is the cross-sectional area, E is the Young's modulus, and L is the length. Okay. We almost forgot about them through all this kind of matrix, all this matrix mumbo jumbo, right? And then we end up with a 4x4 matrix that looks like this. Right? So we're going to have cosine squared, then we're going to have cosine times sine, and then minus cosine squared, and then minus cosine sine. Okay. Then we're going to have sine squared minus cosine sine. And so I'm leaving the first entry in this matrix blank for a reason, and I'll come back to it in a bit. Okay. Then we got minus sine squared. Then we're going to have cosine squared, cosine times sine, and then sine squared. Okay. All right. And so all the entries that I didn't fill in, everything in this lower half, this here is going to be symmetric to what was in the upper half. Okay. And so let's go ahead and fill in the rest of the values here according to its symmetry. Okay. And so let's go in the 2-1 entry first, right? And so this is going to be cosine times sine, because that's symmetric with this guy. Right? Next, we're going to have minus cosine sine right here, okay, because that's symmetric with this guy. Okay. And then we're going to have minus cosine squared, okay, because that's symmetric with that one up there. Right? Then we're going to have minus cosine sine, okay, and then we're going to have minus sine squared, and then we're going to have cosine times sine. Okay. And so, if you want kind of the full matrix where you can kind of just plug and chug, it kind of looks like this. But, once you kind of figure out the first half or the first upper half of this matrix, then you can fill in the rest because it's all symmetric. All right. And so what we have here is, first we have our material properties out in front. So we have our area, our Young's modulus, and our length. And then we have a matrix with a ton of trigonometric stuff. Okay. And so I'll tell you right now that these problems can get pretty tedious because it's going to be a lot of plugging and chugging. And so, you want to be really careful when you're doing these and make sure you plug everything in correctly. Okay. And if you want to check your work, midway, you always want to make sure that your element stiffness matrices are symmetric. Okay. And so if you reflect across a diagonal, you should see, the same thing. Okay. All right. Any questions on this before we do an example? Okay. Okay. So let's do an example to show, how this is actually used. And so in this example, let's consider the following truss element. Okay, so let me draw the stationary axes here. So this is going to be X and Y. And let's say that we have a truss bar that looks like this. Okay, and so this is angled 30 degrees to the horizontal. Okay, and then we'll go ahead and draw the local coordinates in like that. Okay. Let's define its material properties. And so let's say that it has a cross-sectional area of 2 inches squared. Okay. the length is going to be 60 inches. And then the Young's modulus, let's say that is 30 times 10 to the 6 psi. Okay. And so from here, let's compute its element stiffness matrix. Okay. Okay. And so first thing we're going to do is we're going to compute sine, cosine of the angle and sine of the angle, because we're going to be plugging that in a lot. Okay. Okay. And so C, remember, is going to be cosine of the angle. So we're going to do cosine of 30. Right. So cosine of 30 is going to be root 3 over 2. Okay. And then S is going to be just sine of 30, which is going to be 1/2. Okay. All right. And so now that we have C and we have S and we have A, L, and E, we're just going to plug everything into this matrix right here, and we're going to get our 4x4 system. Okay. Okay. Any questions on that before we start plugging and chugging? Okay. All right. And so our K here is going to be AE over L. Okay. And so our A, remember, is 2 inches squared. E is 30 times 10 to the 6 psi. Okay. And our L here is 60 inches. Okay. And then we have our matrix here. Okay. And so our matrix, our upper left entry is going to be cosine squared. And so this can be root 3 over 2 squared. Okay. Next, we have cosine times sine. And so this is going to be root 3 over 2 times 1/2. Okay. Next, we have minus cosine squared. So we have minus root 3 over 2 squared. And then we're going to have minus cosine sine. So minus root 3 over 2 and then 1/2. Okay. All right. So that's the first row. Okay. All right. So second row, I'm only going to write things starting from the main diagonal, and then we're just going to reflect it down afterwards. Okay. And so from here we have sine squared, and so we have 1/2 squared. Okay. Then we have minus cosine sine, and so we're going to have minus root 3 over 2 times 1/2. Okay. Then we're going to have minus sine squared, and so minus 1/2 squared. Okay. And so that's the second row. And then our third row here is we're going to have cosine squared. So we have root 3 over 2 squared. Then cosine sine, and so it's going to be root 3 over 2 times 1/2. Okay. And in the bottom down here, we're going to have sine squared. So it's going to be 1/2 squared. Okay. Okay. And so if we, perform all this arithmetic, then what we get is, out in front, we have 2 times 30 times 10 to the 6. And so that's going to be 60 times 10 to the 6 divided by 60. And so out in front, we just have 10 to the 6. Okay. And in the matrix here, we're going to have the following values. And so first, we're going to have root 3 over 2 squared. And so this is going to be 3/4. Okay. Next, we're going to have, our cosine sine term. So that's root 3 over 2 times 1/2. And so that's going to be root 3 over 4. Okay. Next, we have minus root 3 over 2 squared. So it's going to be minus 3/4. And then at the end, we have minus cosine sine. And so we're going to have minus root 3 over 4. Okay. All right. So I'm gonna go ahead and start filling in the rest of the values, but you can verify these and compute them yourself. Okay, so those are all the values there. Okay, all right. And so now, now that we have all of these values computed, all we have to do is just kind of reflect them over to the other side. Okay. And so first, let's reflect this row. Okay. Okay. And this row, which reads across, we can just go down just like that. Okay. And so first, we're going to have root 3 over 4 minus 3/4, and then minus root 3 over 4. Okay. And so I just wrote that row as the column down there. Okay. Next, let's write this row as a column. Right? Oops. This will be minus root 3 over 4 times minus 1/4. Okay. And then the last entry to reflect is this root 3 over 4 right here. Okay. All right. And then we're done. And so this is the element stiffness matrix for that element. So it's quite a bit more work. So you remember what I said on Tuesday that going to 2D from 1D is not a trivial thing. You can see now that it's not a trivial thing because there's just way more computations to perform relative to the 1D case. Okay. Any questions on this? Okay. All right. So now let's do an example where we kind of put this all together and solve kind of a finite element problem. Okay. Okay. And so we're to consider this 3-element system. Okay. And our 3-element system is going to look like this. Okay. Right, so we're going to have 2 truss elements that go 90 degrees from each other. And we're also going to throw a spring in there because, springs are still a thing. Okay. And so we have this 3-element system. Let me label the elements. And so we'll call this element A on the left-hand side. We'll call this element B. And we'll call this element C. Okay. Let's go ahead and label the angles in between them. So we'll say this is 45 degrees, and this is also 45 degrees. Okay. Next, let's label all the nodes. And so we'll call this node number 1. We'll call this node number 2. We'll call this node number 3. And we'll call this guy node number 4. Okay. And then we also need to put in our load. And so let's say that we have a vertical load here on node number 1. And so we're going to have a vertical load of 10,000 pounds. Okay. Okay. And so let's write out the material properties. And so for elements A and C, so elements A and C are trusses. So elements A and C, their Young's modulus here, let's say it's going to be 30 times 10 to the 6 psi. Okay. Their areas, let's say it to be equal to 2 inches square. And their length, we'll say it's 10 feet. Okay. And element B is a spring. And so for a spring, all we need is its spring constant. And its spring constant is going to be 250,000 pounds per inch. Okay. Okay. And so, you know, here we have our first kind of 2D system. And so what we want to solve for is we want to solve the finite element system for all the nodal displacements. Okay. Okay. And so you can see here we have a 2D system, so it looks significantly scarier than our 1D systems, but you'll see that we follow the exact same process that we've always had. Okay. And so if you think back to our spring and 1D truss problems, always the first step is to write out the element stiffness matrices for all the elements. Okay? Okay. Right, so the only difference here is that our element stiffness matrices are going to be 4 by 4 instead of 2 by 2. Okay. All right, so let's start with element A. All right. And so for these 2D systems, what I find useful is to start by writing out, you know, what's the angle of that element, okay? And that will and then writing out, you know, what's cosine of that angle and what's sine. Okay. All right, so let's start with the angle. So we see element A here, you know, it's a vertical element, right? And so if we compute its angle with respect to the horizontal, it's actually going to be 90 degrees, right? Okay. Because if we compare that to, you know, our horizontal x-axis, which is our stationary x, we had to rotate 90 degrees in order to get to where it is, okay? Right. So this is actually really nice because with theta is equal to 0 or 90, a ton of the matrix is going to cancel out because, you know, we know cosine of 90 is going to be 0, right? And sine of 90 is going to be 1. Okay? And so this makes plugging into the element stiffness matrix easy because a lot of terms are just going to cancel out. Okay? And so what we get is Ka is equal to 5 times 10 to the 5th. Okay? We get that coefficient out in front for doing AE over L. Okay? And then we go ahead and fill in the rest of the matrix here. Okay? Right. And so since cosine of 90 is 0, this entire first row here is going to be 0. Okay. Then we have 0, 1, 0 minus 1. Another row of zeros. And then 0, negative 1, 0, 1. Okay. Right. And then equally as important to the values of the element stiffness matrix, we need to write out which nodal degrees of freedom that they're acting on. Okay. Okay. And so since element A is bordering nodes 1 and 2, we need to fill in the solution vector to have, you know, 1 and 2 there. Okay. Okay. Any questions so far on this problem? Okay. All right. And so now let's do element B. Okay. And so for element B, we see that element B is rotated 45 degrees with respect to the horizontal. Okay. So we have theta is equal to 45 degrees. Okay. And so if theta is equal to 45 degrees, cosine of that angle is going to be root 2 over 2. And then sine of the angle is going to be root 2 over 2. Okay. And so we have KB is equal to. Okay. First thing we have to do is the spring constant, right? And so we're not going to do AE over L because this is a spring. And so our spring constant was 250,000 pounds per inches. And so this is going to be 2.5 times 10 to the fifth. Okay. And then if you plug in, for the angles, you're going to get a bunch of √2/2 times √2/2 terms. Okay, so that's going to give you a bunch of 1/2s. So you're going to have 1/2, 1/2, minus 1/2, minus 1/2, 1/2, 1/2, minus 1/2, minus 1/2. Okay, then minus 1/2, minus 1/2, 1/2, 1/2, minus 1/2, minus 1/2, 1/2, 1/2. Okay. Okay. And then let's write down the nodes that this acts on. And so this is going to be acting on nodes 1, 1 and 3. Okay. Okay. So that's element B. Okay. And so last thing that we're going to fill in is element C. Right. And so element C here, element C is already horizontal, right? And so in this case, theta is going to be 0, right? Because we didn't have to perform any rotation. And so our cosine here is just going to be 1, and our sine here is just going to be 0, okay? Because we're going to do sine of 0, which is just 0. Right. And so Kc here is going to be 5 times 10 to the fifth, because that's the result of AE over L. And then we're going to write out the result of performing all of those arithmetic. Okay, so first row is going to be 1, 0, minus 1, 0, and then 0, 0, 0, 0, and minus 1, 0, 1, 0, and then 0, 0, 0, 0. Okay. And then once again, we need to write out which nodes that they're acting on. Okay. And so this is going to be acting on nodes 1 and 4. Okay. Okay. Any questions on this so far? Okay. All right. So now that we have our element stiffness matrices, now we're ready to apply them to our global system. Okay. So our next step is assembly. Okay. Right, and we're going to need a very large global system for this. Okay. Okay. All right, and so our global system here is going to be 8 by 8 because we have 4 nodes, and each of the nodes are going to have two directives to them. Okay. Okay. All right. And so let's start writing it out. Okay. So let me write out actually the numbers first. Okay. So first, let's write out our forcing vector. And so we're going to have F1x, F1y, F2x, F2y, F3x, F3y, F4x, and F4y. Okay. Right. Then we're going to have a massive matrix here. Okay. And then our solution vector is going to be u1x, u1y, u2x, u2y, u3x, u3y, u4x, u4y. Okay. And let me label the columns here just to make it a bit easier. So u1x, u1y, u2x, u2y, u3x, u3y, u4x, u4y. So I'm quickly running out of space. Okay. And so now let's go ahead and insert our element stiffness matrices here. Okay. Right. And so first we need to insert element A, right? So element A, remember, acted on nodes 1 and 2. Okay. And so let's go ahead and highlight those spaces here. Okay. And so you can see here, I've highlighted a 4x4 block, and that's where all of the node 1 and 2 stuff is going. Okay. Next, let's do element B. Okay. And element B was nodes 1 and 3. Okay. And so we're going to have these ones right here. Okay. First, we're going to have the 1, 1 block. Okay. Right. Then we have the 3, 3 block. Okay. Okay. Then we have that one. Then we have that one right there. Okay. Right. And then finally we have the node what's it? Element C. Okay. And so element C, this is going to be nodes 1 and 4. Okay. And so once again, we're going to have this block up here. Okay. So since they're all connected at node 1, and so the node 1, 1 is going to be pretty busy. Okay. Then we have the 1, 4 block. Okay. Then we have the 4, 1 block. Okay. And then finally the 4, 4 block down here. Okay. And so that's where we're going to insert all of our, element stiffness matrices. Okay. And so if you go ahead and fill in all of the values, you end up with the, and you add, obviously you add the ones that overlap, you end up with the following. Okay. Okay, so you're going to have 6.25, 1.25, 1.25, 6.25, okay? Then you're going to have 0, 0, 0, minus 5, okay? Then you're going to have 0, 0, 0, minus 5, okay? And then 0, 0, 0, 5, okay? Okay. Then in this first green block, you're going to have minus 1.25 and minus 1.25. And then minus 1.25, minus 1.25. Okay. Then down here, you're going to have 1.25, 1.25, 1.25, 1.25. Okay. And down here, you're going to have minus 1.25s. Okay. Okay. right? So those are all the green blocks. And so now let's do all the blue blocks. So in the blue blocks, we have -5, 0, 0, 0, 5, 0, 0, 0, and then -5, 0, 0, 0. Okay. All right. And so all I did there was I just inserted the element stiffness matrices into the appropriate spots. Okay. Okay. And of course, everywhere that we don't have a box here, they're just going to be zeros. Okay. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. All right. And so here is our global system. Okay. All right. Any questions so far on how we assembled this guy? Okay. All right. Okay. And so now that we have our global system like this, we're not ready to solve yet. And so in order to solve, before we can solve, we need to apply our boundary conditions. Okay. And thankfully, in this case, the boundary conditions are fairly simple. Okay. So let's start with our Neumann boundary condition, just like we usually have. Okay. And so if we go back to our problem statement, we have just a single force here, and the single force is being applied on node 1, and it's being applied in the y direction. Okay. And so the way that we can apply this is we can say that F1y is going to be equal to 10,000. Okay. Or in particular, I guess minus 10,000 because it's going in the negative direction. Okay. And so let's go ahead and set this in our global matrix. Okay. And so let's go to the row for F1y, which is the second row right here. Okay. And then let's change that entry to minus 10,000. Okay. Okay. And then since all the other nodes here don't have any forces, we're just going to set their values equal to 0. So 0, 0, 0, 0, 0, 0, 0. Okay. Okay. So that's the Neumann boundary condition. So we have just one here. Okay. And so now we need to apply our fixed support boundary conditions, which is our Dirichlet boundary conditions. Okay. And so if we go back to our problem diagram here, okay, we see that nodes 2, 3, and 4 are fixed. Okay. And so what that tells us is that, all of those displacements at nodes 2, 3, and 4 are going to be 0. Okay. And so all of the rows that are associated with nodes 2, 3, and 4, we're just going to cancel all of those out. Okay. And so nodes 2, 3, and 4 are all of these guys right here. Okay. And so if you remember what we do when we have a Dirichlet boundary condition is that we have to modify the stiffness matrix, right? The global one. And so all of these rows here, the ones that we worked so hard to write the numbers in, we're going to erase them and replace them with, the Dirichlet boundary condition terms. Okay. Okay. All right. And if you remember, the way that we apply these boundary conditions is that we put a 1 on the diagonal. Okay. And so for the third row here, that's going to be in the third column, and then we have zeros everywhere else. Okay. And so that's going to be our new third row. Okay. And so our next row is going to look like this. Okay. And so the 1 has just shifted over 1. Okay. And so our next row looks like that with the 1 in that spot. Okay. And so now we're going to do this one. Okay. And then for U4X, it's going to look like this. And then U4Y, it's going to look like that. Okay. Okay. So this particular problem, this particular problem might be a little bit frustrating because, we spend all that time to fill in all of those entries in the matrix, and we end up just deleting most of it and applying the Dirichlet boundary conditions. So this is a unique case. So usually you won't have as many fixed boundary conditions like this. So you'll have more of your matrix surviving after that. But this one's unique in that we just we had just 3 fixed supports and only just 1 free node. Okay, and so in the end we have this 8x8 system that we can solve, and from here you can put this into MATLAB. So now that you have this 8x8 matrix and you have your 8x1 forcing vector, we can go ahead and input this into MATLAB to solve. Okay. Right. And then once we do that, then we'll have our solution. Okay. All right. So any questions on this before I show you the solution?
No questions.
Yep. Oh, no questions? Okay. All right. And so you plug this into MATLAB and then you get the following results. Okay. And so we're going to have 8 solutions here because we have an 8x8 system. Okay. And so let's start with U1X and U1Y. Okay. Will it always be this miserable? Believe it or not, this is actually not as bad as it could be. And so it's it can be worse. Yeah. Yeah, we'll yeah, it's this part is this part of the class is it's frustrating and it is tedious, but it also highlights why we use a computer for all these things. Yeah, so for in reality after doing this, I think you really appreciate what ANSYS is really doing for you, because ANSYS is doing all of this probably times times a million. Because the complexity of what ANSYS is doing under the hood is a lot more than kind of what we're doing here. So you can see it's a lot of really tedious calculations, and that's why most of the time we have the computers do this for us. But since this is a finite element class, we need to understand what exactly is it that the computer is doing for us underneath the hood. Okay. Okay. And so when we go ahead and plug in this into MATLAB, we get the following solutions. And so UX is going to be 0.0033 inches. Okay. UY is going to be minus 0.0167 inches. Okay. And all the other ones are going to be 0 because they have, those are our Dirichlet boundary conditions. Okay. And that is the solution. Okay. Right. So for homework, so for the homework that I posted for problems 3 and 4, you would basically just follow this exact process right here. So it's a long process. So definitely it helps to definitely start early, but also just stay organized too. So when I've assigned this homework in the past, what people have done is they've kept track of their matrices in either Excel. Or if you want to keep track of them in MATLAB, that works perfectly fine too. Okay, and so definitely use those to your advantage, because as you can see, doing it all by hand, it took us half the lecture just to kind of do this one kind of simple problem. Okay, and so definitely stay organized and use software to kind of help you out, because otherwise it can take a long time. Okay. All right, so question. So would it be better to put the Dirichlet boundary condition first? Yeah, that's a good question. So in if you know that a Dirichlet boundary condition is going to wipe out a lot of your matrix, you can definitely go ahead and do that first, so that you kind of save yourself the trouble to do that. You know, because it's you know, and so you know, I'm not saying that you should follow this exact process here, but the reason I kind of show it like this is, you know, this is actually, you know, the process that most computer codes do. And so, you know, a code like ANSYS, first thing it does is that it forms your stiffness matrix, and then after that it applies your boundary conditions. And for, you know, for more complicated problems, especially, you know, in 3D, this actually is better because it kind of helps you stay more organized. But for these problems, I know that since they can be really long, you know, if you know that a Dirichlet boundary condition is going to wipe out a lot of your system, you can go ahead and apply that one first. Yeah, just make sure you note that in your work too, so that, you know, because there's a Dirichlet boundary condition here, I know I'm not going to bother writing out these entries in the matrix. Yeah. Okay. Any final questions on this? Okay. All right, so I'll end it just a 1 minute early today, because, you know, I don't want to get into the rest of this, but we have maybe about half a lecture's worth of material left in these Truss notes, and then we're going to move on to the next structural element that we'll learn, which are beams. Okay. All right, so that's all I got for today. Happy the internet kind of stayed active for the entire lecture today, and so have a great weekend, everyone. It's a long weekend, so, you know, definitely relax on that Monday off if you can. And so, you know, even though, you know, we don't meet on Mondays usually, but I will have my office hours on Monday. And so if you want to come by, you know, Monday morning, 9 to 10, I will be there. But otherwise, Monday is a holiday. So, you know, take it off, you know, relax a little bit, enjoy Lunar New Year if you celebrate that, and Valentine's Day. So it's a busy weekend for a lot of us, right? And so enjoy the rest of your evening, and I'll see you guys on Tuesday.
Thank you, Professor.
Thanks,
See you
guys.
next week.
Thank you.
Thank you. Have a nice weekend.
Thank you. You too.
Thank you.
Thank you.
Great. Simon, do you have any other questions? I guess I'll see you in 4:42.
No, I'm
afterwards.
okay. Thank
Okay.
you.
All right. Yeah, I'll see you.
Bye.
I'll see you in 40:42.
Yeah, I'll see you in a little bit.